Question 8.5 deals with hydrohalogenation, and it says predict the products for each of the following reactions. In some cases, the reaction produces a new chirality center, while in other cases, no new chirality center is formed. So if I take a look at the first molecule, it's an alkene, it's unsymmetrical, and I'm treating it with HBr. And I'm going to go by the Markovnikov rule, which states the rich get richer. This is the only carbon that has a proton attached, so that's the carbon that's going to take the proton from HBr. So I like to draw the curved arrow from my pi bond through that carbon just to designate that's the one the proton is going to. So let's draw the carbocation. So here's my carbocation. It's a tertiary carbocation. It will not undergo any kind of rearrangement. So now my nucleophile, the bromide, it can attack from either face of that molecule because that carbocation is sp2 hybridized. It's trigonal planar. So I can draw a curved arrow in here if I want, like that. And I'm going to end up with a racemic mixture in this case. So I'll draw the first enantiomer like this. And then I'm also going to get this enantiomer as well. There we go. So I'm going to get the R and the S. All right, so I get a mixture of enantiomers. In the second example, again, I have an unsymmetrical alkene. There's only one hydrogen attached to either of the carbons in that double bond. So I'm not going to draw the mechanism for this one. I'm just going to go by the rule, the rich get richer. So I'm going to do my protonation. So there's my carbocation. It's a tertiary carbocation. And in this case, when the chloride attacks, it doesn't matter which face of the molecule it attacks. I end up with an achiral compound. So I'm going to end up with this alkyl chloride, which is achiral. So I only get one product in this case. Let's take a look at the last one. So again, an unsymmetrical alkene. There's only one hydrogen for either of the two carbons in the double bond. So I'm going to draw the curved arrows just for fun. So I'm going to draw my curved arrow like this. And then I'm going to draw my carbocation. Oh, it's a tertiary carbocation. And of course, the iodide can attack from either face of the molecule. And I'm going to get a mixture of enantiomers. And it's going to be pretty much an equal mixture. Not entirely, but I'm still going to get the two enantiomers. So I'm going to get this one, and then I'm also going to get this product as well. So draw the second enantiomer, and there we go. So we figured all of those out. We used Markovnikov's rule, and we decided when we were going to get a new chiral center, we got both enantiomers, and in this example here, we have an achiral compound, so there's only one compound produced. Let's take a look at one more mechanistic question. So it says here, draw a mechanism for each of the following transformations. Well, there's only one, so let's just do that one. So let's do the first step, and that's going to be the double bond, taking on the proton from HBr, again, following Markovnikov addition. So I'm going to draw the carbocation that I would get. Again, I'm following the rule, the rich get richer. This carbon has two hydrogens attached to it, and this one only has one attached to it. So I'm going to draw my carbocation. It's a secondary carbocation. So let's write down there, secondary carbocation, but there's a proton right here. And if this undergoes a hydride shift, I end up with a tertiary carbocation, which is more stable. So then in the last step, to give me the tertiary alkyl bromide, my bromine, or my bromide is going to come in as my nucleophile, so I'll just draw my curved arrow like that, and that's going to give me the final product. So there we go, a little bit of mechanistic practice for our Markovnikov additions, and also an example of a hydride shift.